Hey guys, today we're going to go through kind of part one of what falls under hydrolysis of salts. So basically how the ions in a salt interact with water and how that leads to a couple of scenarios. So just to bring you back to kind of where this originates from is we mentioned or talked about at the beginning of this unit that acids and bases can react to form water in a salt. And you may have heard me mention to you that, people kind of have this misunderstanding that whenever an acid or whatever base react together, form water and salt, and it's neutral, which is sometimes true. However, it really has to do with the salt that gets produced that's still in water and how that salt interacts with the water that's present. Now, the times where that acid and base reacting to form water and salt do actually form a neutral solution is when the anion and the cation of the salt originate from or come from a strong acid and a strong base. So whenever you have a strong acid and strong base reacting, it's going to produce this neutral solution, and it really has to do with the fact that that salt and those ions are not going to be able to interact with water at all, which then allows the salt to stay neutral or help the solution stay neutral. Now, that's not always the case though. So we do have salts that will yield an acidic solution. And this occurs when we have the anion of a strong acid and the cation of a weak base. Now, when we kind of look at a shortcut for this, how I kind of initially teach this to honors, is you think of, okay, well, those ions come from a strong acid and a weak base. So you kind of think of, oh, well, the strong acid wins out and you get this acidic solution. And that's a great little shortcut to just figuring out what type of solution you have, in this case, an acidic solution. But it's really not the strong acid that causes the acidic solution. It has to do with the cation of the weak base. So if we look at this salt, ammonium chloride, when it dissociates, forms ammonium and chloride ions. Now, those chloride ions, you can kind of think of originating from HCl, okay, which is a strong acid. So the chloride ions can't interact with water because if it reforms HCl, HCl is a strong acid, you think of it immediately ionizes back to the chloride ions. So the chloride ions aren't able to interact with the water molecules and affect the solution's pH at all. However, the ammonium ions, or the cation of the weak base, will in this case. So the ammonium is going to interact with water. And when it does that, in this case, it's going to donate a proton to water. And when it does that, it's going to form its conjugate, which is NH3 ammonia, and then it's going to produce hydronium, H3O+. Okay, that's what is actually forming that acidic solution, or why we get a pH less than 7, is because of the ammonium ion acting as an acid and donating a proton to water. So I definitely would say you need to know kind of the shortcut. How do you come up with the fact that those ions come from a strong acid, weak base and produce this acidic solution, but then also being able to write the equations to explain why that acidic solution is actually produced. And then we do have salts that also yield a basic solution. So this is when we have the anion of a weak acid, the cation of a strong base. Again, kind of the initial little shortcut here is when we look at the ions, we see, oh, they come from a weak acid and they come from a strong base. The strong base wins out, so we get this basic solution. And again, yes, like I said, that's a great way to kind of simplify it initially to know that you're going to get a basic solution, but it really actually is affected by the anion of a weak acid. So if we take sodium acetate, we have the acetate ion that's going to dissociate into water, and then the sodium ion. And again here, you can think of that sodium ion as being from sodium hydroxide, a strong base. The sodium ion isn't going to be able to interact with water in any way, so it's not going to affect the pH of the salt solution. However, it's really the acetate ion, the anion of the weak acid, that's going to produce, our basic solution. So when we look at the acetate ion interacting with water, in this case, our acetate ion is going to accept a proton from water. Okay, when it does that, it forms its conjugate, acetic acid, which we know is a weak acid, and then hydroxide. So it's this production of hydroxide which contributes to the basic solution. So again, you want to be able to know when we look at the anion and cations that in this case, it's coming from a parent weak acid and strong base, which results in a basic solution, but it's really because of that anion of the weak acid and how it interacts with water to produce hydroxide that's going to cause that basic solution. When we have it forming from, if we have an anion of, let's say, a weak acid and the cation of a weak base, it's actually, you can think of it as being unknown. You have to look at the Ka and the Kb and compare them in order to determine it. So just like a little note, I'm going to come back to that, but just in case you're wondering, well, what happens if they're both weak? We can figure it out. It just takes a little bit more work. All right, let me just go through kind of the initial examples of what I want you to be able to do, and then we'll look at a couple other ones that go a little bit farther. So here we have our salt, potassium bromide. We want to know what type of solution is it going to form, either when we dissolve the salt into solution or if that was the salt produced from a reaction. So you can think of, we have our potassium ion and our bromide ion. So the bromide ion, if you think of its parent acid, and it's that anion that would have, you can think of it's coming from the addition of the hydrogen ion, this would have been from HBr. Okay, the potassium ion, and think of the parent base, is having hydroxide, and there are some exceptions to this. That negative ion would go with the positive ion, and so you can think of the parent base as being potassium hydroxide. So again, this is just kind of a way to figure out what type of pH this salt could potentially have in solution. So HBr is a strong acid. Okay, potassium hydroxide is a strong base. So the cation and the anion of the salts are both not going to be able to interact with water, and because of that, it will produce a neutral solution. Okay, and again, you can think of it as, okay, you have your strong acid, strong base, that results in that neutral salt solution. So in this next one, we're going to see that we can think of it as the parent acid being HF, and then we have sodium hydroxide. HF is one of our weak acids. Sodium hydroxide is a strong base. Okay, so in this case, we can, based on the parent acid and base being a weak acid and strong base, we would know that this is going to be a basic type of solution. Now, the explanation for that is if we have the fluoride ion, which is going to interact with water, and you could put this anywhere on the paper, okay, it's going to accept a proton from water to form that weak acid, and then because of that, you get that hydroxide in solution, and it's that hydroxide that leads to that basic solution there. All right, in this next one, we have H2SO4 and KOH. Okay, sulfuric acid is a strong acid. KOH is a strong base. So because we have strong and strong, this would be a neutral solution. Okay, moving on to our next one. Here we have HCl. Now, a lot of students will write like ammonium hydroxide, okay, which would result in the same kind of explanation here. But up above, we showed that ammonium is really, its parent base here is really going to be NH3. Okay, so HCl is a strong acid, and then ammonia, NH3, is a weak base. Okay, so if we have a strong acid, weak base, we would expect an acidic solution. And again, the reaction that supports that would be, I'm going to kind of be writing this, over here where I have a little bit of room. I have my original ammonium ion from the salt that's in water. It's going to be reacting with water, which then it's going to donate a proton to water to form that ammonia, and then the hydronium. Okay, that should be AQ. Okay, that hydronium is what results in that acidic solution. All right, and then the last one on here, we have HClO4 would be our parent acid, which is one of our strong acids, and then zinc. A lot of students will write like your zinc hydroxide, which it's not group 1 or group 2, so we know then that would be our weak base. But really, those zinc ions, when we talk about how they interact with water, goes back to a previous lesson where we talked about how zinc ions will become hydrated with water, usually 6, and then include the charge. It's that setup that's going to actually give us the hydronium that we would expect. So if we have a strong acid, weak base, we would expect it to be acidic. But how it actually produces that is a little bit more complicated. So we would have the zinc ions with the 6 water molecules surrounding it. I'm just going to leave out phases for space here. If you remember, what we talked about was that should be reversed. The charge of the zinc ion, so this how small it is and the charge of it, is going to affect the polar bond of the hydrogen to the oxygens, so that one of those hydrogens actually gets ionized by another water molecule that approaches it. So the zinc then loses, or the water molecules around zinc lose a hydrogen ion, and then we have the formation of the hydronium there, which supports the fact that we would expect an acidic solution. Okay, so really initially you want to be able to just identify what type of salt solution would we have from that salt, but then also being able to justify it based on those reactions with water. I only have like 3 minutes before this video has to end, so I'm going to quickly just point out a couple other things that you can look at the end of this section for, so that you can just see what I'm talking about with this one. So here we have ammonium chloride. So when we talk about that dissolving, we have our NH4 and our cyanide ion. Okay, both of those come from weak acids and bases. So the ammonium, when that interacts with water, would form ammonia, and it's going to donate, so it forms the hydronium. Okay, the cyanide ion, when it interacts with water, water is going to be donating a proton to the cyanide ion to form HCN, and then you form hydroxide. So we would have to look at, because they come from, again, this case would be a weak base and a weak acid. There's no like easy, like, oh, this is the type of solution. We have to know, well, how much hydronium gets produced, how much hydroxide, and which one is there more of, in order to kind of go about this. Now, I'll talk tomorrow about the actual values of this and how we got them, but just because of time, we have NH4 and CN. For NH4, we end up figuring out that the Ka 5.7 times 10 to the negative. Oops, read my handwriting. Negative 10 here. The CN ion, which is acting as a base, its Kb is 1.6 times 10 to the negative 5. So the Kb here is greater than the Ka, so we would expect more hydroxide to be produced. So we would expect this to form, in this case, a basic solution.